All right, guys, I want to go through some of the multiple choice problems that I gave you as practice for this particular section over solids. Again, one of the more difficult portions of this chapter is actually just the problem-solving aspects of it. So let's look at this first one. Fairly long problem, takes up the full page, very stereotypical college board. Let's look at it and see what we can do. So it says steel is an alloy consisting of iron and a small amount of carbon. So what we pay attention to is, first off, alloy. We know there are two different types of alloys. We have interstitial, which I'm just going to abbreviate as IN, as well as our substitutional. Whoops, not sure why it just freaked. Give me 2 seconds to pull that back up. There we go. There we go. So notice iron and carbon, two different sizes, so chances are we're looking at interstitial, but let's keep reading. Elements of chromium can also be added to the steel to make the steel less likely to rust. Chromium atoms react with oxygen in the air to form a non-reactive layer of chromium oxide on the surface of the steel, preventing the oxidation of underlying iron. A sample of steel chromium alloy contains 15% chromium by mass. Which of the following diagrams best shows a particulate level view of the surface section and the interior section of the alloy represented below at the left? So notice here we're given molar masses, which is for this 15% part of it, as well as the atomic radius aspect of it. And notice here we're told carbon is 77 ppm, picometers, and iron is 125. So big difference in size here. So again, that tells us we're going to be dealing with interstitial in that regard versus iron and chromium, 125 to 127. Very, very similar, so we're going to be dealing with substitutional. So let's kind of go through and look at our pictures and see what we can come up with. First off, we're told that this left-hand side is surface level. So if we go back up and kind of read what we're looking for here, at the surface we're looking for this chromium oxide that they're referring to as a layer on the top. And then we're also looking for iron and carbon to be in the interior layer, which is our right-hand picture. So let's kind of scroll down and see what we got. First off, the surface here. If we look at this, this is purely iron and oxygen. We don't see any chromium present whatsoever. So we can kind of go ahead and rule that out. That's not going to work based off of what we just read. Same when we read this one, we got the iron and carbon, which actually is what we're looking for because it is interstitial, if you notice. So that could work, but this first picture doesn't work, so we can roll it off. Moving down to the next picture, we've got carbon mixed in, which is what we would want to see because it is an alloy, so it's going to be evenly mixed. Again, forget the baby noises, sorry. And then at the surface, we see this chromium and oxygen layer. We see a little bit of those chromiums mixed in, so that's a possibility. Okay, over here, again, we've got the iron and carbon mixed in. Again, could be a possibility. We'll leave it alone for right now. We're not going to rule it off. Keep scrolling down. Okay, over here, notice where the chromiums are. The chromiums are actually interstitial, which is not going to happen because they're similar sizes. So we can go ahead and rule that out. And those CRs might be a little bit hard to see, but they are there. Same with this one where the CRs are. We can rule it out. Okay, down here, again, we've got our iron and carbon mixed in. We've got our chromium and our oxygen layer on the top, so that's a possibility. Let's check out over here. Notice over here in the interior, we've got oxygen in the interior. That's not going to happen. Remember, what we're trying to do is get the chromium and oxygen to bond on the surface level, not have oxygen in the center. So we're going to go ahead and rule it out for that reason alone. Okay, so what that means is our best answer is actually this B right here. And again, the reason being is we have the chromium and iron substitutionally mixed in. We've got the carbon, which is interstitially mixed in, and the carbon is going to be both at the surface and in the interior due to the fact that it is an alloy. Remember, alloys are basically solid solutions, if you will. So they should be homogeneous, basically mixed evenly throughout. We've got the oxygen layer at the surface, no oxygen in the center, and that's basically our reasoning. Okay, so moving on. This one's very similar to the one you had in the notes. Which of the following can be the identity of a white crystalline solid that exhibits the following properties? Melts at 320, so fairly low. I'm not going to put lowest or anything like that, but just kind of note that that's a fairly low melting point. Does not conduct electricity as a solid and does not conduct electricity as an aqueous solution. So again, if we kind of go back through and think about this, we have molecular solids. which have our lowest melting points. They are not going to conduct electricity in any way, shape, or form. So that looks like that could be a winner. We have our ionics, which will conduct electricity as an aqueous solution, so we can rule that out based off this last bullet point right here. We have our metals, which will conduct electricity as a solid, so we can rule that out. And we have our networks, which again will not conduct electricity in any way, shape, or form. But they also have extremely high melting points, so we can rule that as well. So we're looking for a molecular solid. We go through. C6H12O6 is a sugar, so that's going to be molecular. I'm going to put an M next to it. Actually, I'm going to put MOLE for, not to be confused with mole, but for molecular. We have sodium hydroxide, which is ionic, so I'm going to put an I. Silicon dioxide, which is a network, so N. And copper, which is a metal. Okay, so our best answer is A. Okay, 3. I made a note at the top of 3 for a reason. You need to use Coulomb's law. It hasn't just magically disappeared, even though we haven't talked about it recently. Based on the data above, which of the following statements provides the best prediction for the boiling point of sodium chloride? So, back up, rewind. Let's discuss this again. Sodium chloride is an ionic compound. What makes ionic compounds, or what holds ionic compounds together? Well, it's electrostatic attractions. Okay, and technically all attractions, whether they're inter or intra, is based off of Coulomb's law, which remember is Q1, Q2, so these are our charges, over R squared. And this is actually something we did discuss a little bit last semester, so we're just going to kind of bring it back in. And remember, this equals either the force of attraction or force of repulsion. In this case, because we're dealing with opposite charged ions, we're looking at a force of attraction. Q1, Q2 is our charge, so the higher the charges, the higher the force of attraction because it's on top of the fraction here. It's our numerator. And then our denominator is radius. The larger the radius, the smaller the force of attraction, or the smaller the radius, the higher the force of attraction, however you kind of want to think about that. So what we're looking at here is the size of the atom. So notice you have those right here. And then also the charges of the atoms. And then we have those boiling points. So we are looking at the boiling point of sodium chloride. Given the boiling point of sodium fluoride is about 1700 and magnesium oxide is about 3600. Again, let's kind of break this down and talk about the reason why. So if we look at the ionic radius for sodium, it's about 76. If we look at it for magnesium, about 72. So those are very, very similar. Fluorine is 133, oxygen 140. So again, very, very similar in terms of ionic radius. So I would say our R squared for both of these salts are very, very similar. The difference is going to be our Q's. Sodium fluoride is going to be 1 and 1. Magnesium oxide is going to be +2 and -2. So larger numerator is going to give a higher force of attraction. Higher force of attraction means more energy required to break, resulting in a higher boiling point. So with that in mind, let's check out sodium chloride. Sodium chloride, we have 76, again, very similar, or exactly the same as the sodium, very similar to the magnesium. And then we have chlorine, which is 181. So that is an increase in radius in compared to our fluorine ion. So that means we are going to increase our radius here, which is going to decrease our force of attraction. Also keep in mind our Q1s and Q2s are still 1 and 1, just like they are with the sodium fluoride. So the big thing here is recognizing that sodium chloride is going to have a smaller boiling point than sodium fluoride, and magnesium oxide is still going to have a larger boiling point due to the fact that it's got the smaller radiuses, or similar radiuses to sodium fluoride, but smaller than the chlorine ion, and then the higher charges. So with that in mind, let's see what we got. A. Sodium fluoride will have a lower boiling point than sodium fluoride because the cumulative attractions are weaker in sodium chloride than sodium fluoride, so that's what we just discussed. That sounds like a winner. Sodium chloride will have a boiling point between sodium fluoride and magnesium oxide because of the covalent characteristics of the bond. Okay, well that word right there tells us we can rule that out. Electrostatic is not covalent. Okay, sodium chloride has a higher boiling point than magnesium oxide because the ions are spaced farther apart. Does that make any sense according to our Coulomb's law? No. Coulomb's law says the more spaced out they are, that means a larger radius, larger denominator, smaller force of attraction. And then sodium chloride will have a higher boiling point than magnesium oxide because the energy required to transfer electrons from the anion to the cation is larger. So time, they're already ions, they've already transferred electrons, that has nothing to do with anything. So we're going to rule that out as well. So our best answer is A. Okay. Next one's also going to be dealing with Coulomb's law. Again, it hasn't gone anywhere. It is still something you need to be able to utilize So based on the data above, which of the following correctly predicts the relative strength of attraction, the zinc ion, calcium ion, barium ion, ions with water. Okay, so first and foremost, this question does not belong on this worksheet, and I'm sorry, I'm just now realizing it. I'm going to go ahead and leave it on there because it's something you can answer. This is actually dealing with a little bit later on when we talk about solutions, which we've already talked about to some extent or another. So let's go ahead and answer it and see what we can do. It's still based off of Coulomb's law, Q1, Q2 over R squared. The difference is now we're looking at an ion of some sort with the attraction to water. Again, this attraction is all based off of Coulomb's law. Coulomb's law is the governing factor on inter and intramolecular forces. Okay, so if we're looking at zinc, calcium, and barium, zinc has got our smallest ionic radius, calcium's in between, barium is our highest. That means zinc is going to have the stronger force of attraction, and also keep in mind they all have +2 ions, so charge plays no factor here. Zinc is going to have our smallest radius, therefore highest force of attraction. Barium is going to have our largest radius, therefore weakest force of attraction. So I would say we're looking for zinc, calcium, and barium in that order, so we're going to rule off C and D. And then we're going to look at our answers. Because the smaller ion has a stronger Coulomb-like attraction, yes. Or because the smaller ion has more electronegativity, no. So answer's A again. So again, we're not quite there in solutions yet. I apologize for leaving it on there, but it is something you can totally answer without too much of an issue. Okay, moving right along. Okay, question 5. To make gold stronger and harder, it is often alloyed with other metals such as copper and silver. Consider 2 alloys, one of gold and copper and one of gold and silver, each of the same mole fractions of the gold. If the gold-copper alloy is harder than the gold-silver alloy, which of the following is the best explanation on the information in the table above? So again, notice here we're given melting points of the different metals, we're given atomic radiuses, we're given oxidation states, which really don't play any role here, because remember what we're dealing with is, in actuality, alloys, which are the pure atoms covalently bonded together. So we really don't care about this oxidation state in any way, shape, or form. We care about these 2 species right here. So let's kind of look at our answers and see what we come up with. Copper has 2 common oxidation states, but silver has 1. Has nothing to do with it. We're dealing with an alloy, which are the pure metals. We're not dealing with anything in terms of ions, so we don't care about their oxidation numbers at all. Copper has a higher melting point than gold, and silver has a lower melting point than gold. Okay, so let's just kind of break that down. We're told that the gold-copper alloy is harder, and then the gold-silver alloy. Sorry, I'm having a hard time saying alloy right now. So could melting point play a factor? Maybe, so we'll leave that in there. We're not going to rule that one out just yet. That could be an option. Copper is smaller than silver, thus they interfere more with the displacement of atoms in the alloys. So again, when you're dealing with size here, notice that gold and silver are very, very similar, and even gold and copper are very similar to each other as well. So in terms of displacement, they're both probably going to be substitutional alloys. So probably not the best answer in the world. We're going to go ahead and rule that one off as well. And then copper atoms are less polarizable than gold or silver atoms. Thus, copper has a weaker interparticle forces. Okay, or intermolecular forces is where they're going there. Again, that could be a reasoning in the fact that it is less polarizable if it has less electrons, which copper technically does. But here's the problem with this. Copper has weaker forces, would not be making it harder. That would actually be making it weaker, so we can rule that out as well. So our best answer here is really this B, the fact that the melting point here is what's making it harder, because copper has a higher melting point. Okay? Last one but not least, just very quickly because I'm about at the 15 minutes, which one shows cleavage? Cleavage, remember, in ionic compounds is when charges are next to each other, so A automatically is that answer. B doesn't make any sense. If you notice, it's taking 2 plus charges and slamming them together to make +2. Well, that doesn't happen in real life. Down here, you're looking at the metals, and notice what this is really showing is more of that ability for the metals to mold and move, so that malleability and ductileness. And then down here, I'm not really quite sure what they're trying to show here, but it looks like it's probably a molecular solid. So again, not what we're looking for. So just A on that. And that's it for the multiple choice section. Thanks, guys.